be here to talk about this growing and, as Anne said, elusive class of ambiguous nuclear transients and some of the things that we've learned about them so far, as well as some of course, the open questions in future research to try to address them. And so throughout the conference, we've heard quite a good motivation for trying to select a clean sample of TDEs, where clean here typically means trying to move things that are known AGNs, whether that's through some sort of optical or infrared color selection, or things like the BPT diagram when we're trying to remove things that have ionization conditions that are more consistent with the typical AGN. And obviously these types of things are very important, right? If we're trying to study just TDE physics and understand, for instance, what's powering the UV optical emission or any number of the long list of questions remaining for TDEs, of course we need to try to select things that we're really, really sure are TDEs. But that obviously means that we're going to miss any sort of TDEs that exist in AGNs, and of course, we do expect those to happen. And these have been a source of some theoretical interest over the past few years, with several people doing hydrodynamic simulations of these types of events. And broadly speaking, there's a few key characteristics that we find from these. One, that the observables are complicated, and we don't really know, but that they should depend, of course, both on the AGN disk conditions prior to whatever event, but also how the TDE happens with respect to the disk, whether it's a prograde event with respect to the disk angular momentum or retrograde. And as we heard yesterday, there's even more reason to look for TDEs occurring in AGNs because perhaps they enhance the rates quite a bit. And so maybe we're missing even a reasonably high fraction of the total TDE population by focusing on things that are not AGN host galaxies. And so with this, I just want to set the stage just a little bit more for context of the two main classes of accretion onto black holes that I'll keep drawing comparisons back to. The first, of course, is these active galactic nuclei, which are the more quasi-statically accreting black holes over time. And a few of the key observational parameters, right, are ubiquitous X-ray emission and emission across their electromagnetic spectrum that's reasonably well fit by a power law. They tend to show both narrow and sometimes broad emission lines, as well as the hallmark of AGNs, which is their stochastic variability. On the other side are the TDEs that we've heard so much about, right? They only sometimes show X-ray emission, and when they do, it's not particularly hard. The UV optical is also well fit by a black body, and they typically only show broad lines, and rarely, if ever, do they show stochastic variability on the flare, although, of course, you've heard about repeating or rebrightening TDEs, but it's not the same type of stochastic variability that we expect from, say, an AGN disk. And so you might think that these two are completely dissimilar, and of course that's generally true, but we've found this class of objects that seems to share some of the properties of AGNs and some of the properties of TDEs, and these are, of course, the ambiguous nuclear transients, or ANTs. And so throughout this talk, I'm going to show a lot of different comparison plots, and I'll keep this kind of color scheme of red things are more AGN-like, blue things are more TDE-like, and then the purple, of course, is this ANTs that are sitting somewhere in between. And so what better place to start to try to understand these ANTs than looking at their host galaxies? Obviously, a lot of transients, the host galaxies are telling us something about what might be happening. And so actually returning to this idea of the color selection, here I'm showing this WISE 4-color infrared selection. And when we put the ANT hosts on this diagram as compared to a few other TDE hosts and a field sample of galaxies in these black points, we see that relatively few of the ANT hosts are clear strong AGNs. They are a little bit redder, definitely than the TDE hosts, and indeed many are consistent with redder colors than a typical galaxy. And so I think this is suggestive of these galaxies hosting at least some sort of weak AGN, where that AGN power law is giving a bit redder color than you might expect just from the stars in the galaxy. If you look at the X-rays of the events prior to the flare, at least for the ones that have good enough observations or existing X-ray observations to do this, of course TDE hosts rarely, if ever, show X-rays. Partially, of course, this is a bias that we're selecting against this. But about half of the ANT hosts show X-rays prior to the flare. Some of them are immediately consistent with being an AGN in the first place, but even the ones that aren't are well above what you might expect from, say, X-ray binaries in the host galaxy. And so there's probably something else, a low luminosity AGN, or even in some cases, of course, a much stronger AGN in these galaxies. And that's not a surprise. I already told you this. When we look at the stellar masses of these host galaxies, we see that they're generally a bit more massive than TDEs, and indeed some of them host black holes that are starting to push to the Hills mass and above for a solar mass star. And so, of course, there's something else probably going on here than just a normal TDE. And that's not surprising, as we'll go through, that the properties are quite different. And so I'm going to now switch, of course, from the host galaxies to the ants themselves, walking from the highest photon energies down to lower energies as I go through the talk. And in the X-ray, as compared to TDEs, ants show much harder X-ray spectra. And in some cases, they're quite hard, approaching a photon index of 2 or even harder. And even when they are softer or show some sort of thermal spectrum, as in the case of a 2019 PEV over here, they still show a hard power law tail that tells us that there's likely some non-thermal contribution to the X-ray spectrum. And so going beyond just the spectra to the light curves, we see that, broadly they're consistent with the TDE picture, both in luminosity and evolution, although some of the ants, like the very well-studied Assassin 18EL over here, have very, very long-lived X-ray emission, quite different than you expect from TDEs. But again, the picture here is that the X-ray luminosities are fully consistent with the AGN-like picture that you tend to see. In terms of their UV optical emission, they're generally well fit by a blackbody and show a range of peak luminosities more or less comparable to TDEs, in some cases quite a bit more luminous, which is perhaps not surprising given they're more massive black holes, but also some of them are quite a bit less luminous than the least luminous TDEs that we have so far. But interestingly, regardless of their peak luminosity, they seem to show a really flat evolution of this luminosity in time, whereas, as I'll return to in a bit, the lower luminosity TDEs kind of fall off very quickly. These ants continue to emit at more or less the same luminosity for quite a bit. In terms of their effective radii, they're generally similar to TDEs, but sit at a bit higher effective radii, and their temperatures are similar, but on the cooler side. But I will note, of course, that their temperature evolution, again, is pretty similar to TDEs in that it's roughly flat in time. And so we're seeing a more or less consistent picture with these TDEs and ants in the UV optical, at least on broad strokes comparisons here. Returning to this point of the after peak luminosity decline, we see that the ants don't show this nice trend that's been seen for the TDEs, where the more luminous TDEs at peak are declining more slowly. Here, delta L40 is just a delta M15-like parameter. That's the luminosity decrease at 40 days after peak. And so we see this trend again where the more luminous TDEs decay slowly, the less luminous TDEs fall off quite rapidly. But when we look at the ants, regardless of their peak luminosity, they're all decaying very slowly, and indeed more slowly than the average TDE seems to be decaying. And so what I think this is immediately telling us is that if we assume that this type of TDE correlation is driven by the fallback of mass onto the supermassive black hole, and I should note that the slope is roughly similar, and so that's probably what we're seeing here. This is telling us the ants can't just be driven by the fallback of mass onto the black hole. There has to be some other mechanism that's changing their decline rates. If we take the X-rays, which as I mentioned are a little bit more AGN-like, especially their spectral properties, and compare that to the UV optical, which again is more TDE-like, we might try to understand how they sit in this kind of parameter space with the ratio of the two. And again, no surprise, some of them are very similar to AGNs in having a ratio of the optical to X-ray luminosity between maybe 0.1 to 10% or so. Excuse me, a factor of 0.1 to 10%, or 10 times. But more broadly, the ants are quite similar to the TDEs. Some of them, like Assassin 18JD and Assassin 20HX, are well above what you might expect for a typical AGN, being very optically dominated. And so I think that the picture here is that the ants and the TDEs, at least in this parameter space, are quite consistent. There's some differences, of course, in their spectral behavior and the peak luminosities, but they're not too similar or dissimilar in this space. In terms of their spectra, they're obviously quite a bit different than TDEs. This is partially why they're the ambiguous nuclear transients, but they do show some similarities. They're persistently blue throughout their evolution, and they do show many of the broad lines of hydrogen and helium that we tend to see in other TDEs and nuclear transients. Although, of course, given that they are AGN host galaxies, many of them do show these narrow cores of the lines that are consistent with potentially AGN ionization. But I think this picture tells us that we are seeing some sort of accretion onto the black hole. It's not just that we're seeing, perhaps maybe with the case of Assassin 15LH, although I'm sure many people would disagree, we're not seeing just extreme or exotic classes of supernovae. It's very likely some sort of accretion onto the black hole that we're seeing in these events. Finally, looking at the infrared, we see that all of the ants show a very large infrared flare, implying some sort of dust echo from the initial UV optical transient that we see. And if we compute a covering fraction roughly by taking the peak infrared luminosity to the peak UV optical luminosity, we see that they live at a few tens of %, which is both consistent with the typical AGNs at a range of black hole masses. And so I think, first of all, this is telling us, of course, again, independently confirming that they are living in AGN host galaxies, and we're probably seeing the dusty torus of this AGN being irradiated. But also I'll note that they're very interestingly similar to many of the mid-infrared selected events, whether that's Megan's sample of the infrared selected TDEs, or other samples like the Myrongs that are just selected based off of their infrared properties without caring about what particular host galaxies they live in. And of course, as you can see here, there's quite a bit of a difference between these ants and the other mid-infrared selected TDEs, as Megan said, from the typical TDEs that are living in very, very dust poor environments. And so putting this all together, I think there's a few things that we already know pretty well about the ants, which is that they are transients occurring in an AGN host galaxy of some variety. Some of them are low luminosity AGNs, some of them are a bit higher. There are also luminous events across the electromagnetic spectrum, at least the UV optical and X-ray and infrared. And I think in particular, the fact that we see this luminous X-ray emission really drives home the point that they must be some sort of accretion-esque phenomena related to black holes. And finally, this point of the more massive black holes tells us that they're probably not typical TDEs. We already know that. There must be something else going on, which of course brings me to the open questions for this class. And I think one of them is, what are the actual rates of ants? At least observationally, taking the known number of ants and the known number of TDEs, given that they're selected similarly, I think that's at least a 0th order fair comparison. It's somewhere around 10%, which I'll note is an interesting number given that about 10% of galaxies host some sort of low luminosity AGN or so, might just be telling us that maybe these are TDEs and AGNs. But the problem here is getting a clean selection. As they are ambiguous, it's a bit difficult to define a clear criteria and know what we want to include and actually compute a robust rate and compare that to the other rates of TDEs that we've heard from earlier in this conference. But then I think the million-dollar question, of course, is what's actually driving the luminosity we see? If they are some sort of exotic TDE, maybe it's just the disrupted stellar mass and the higher mass black holes are giving us a very different transient. Perhaps this is the type of picture from McNernan et al. And many others that have looked at TDEs and AGNs where we have some sort of star get very close and tidally disrupted, but we're also sweeping up mass in the disk that eventually accretes on, and that's changing both the timescales and the observables. Or perhaps they're not AGNs, or excuse me, TDEs at all, and we're just seeing some sort of AGN disk instability that we're now sensitive to with these long baseline and high cadence optical surveys. And so, of course, this is the key question that we really need to answer to understand, what are ants and how do they fit into this picture of nuclear transients more broadly, but the comparison to TDEs. And so now that I've set the stage and talked quite a bit about these ambiguous nuclear transients, I want to quickly draw some comparisons to some, I'll say, tenuously related events. The first being the QPEs that we've heard about. Obviously, the mechanism is not the same here. I'm not even suggesting, of course, that the physics are the same. But there is this interesting connection that, of course, we have some belief that the QPEs are coming from events where you have a pre-existing disk and you have some interaction there. And at least my suggestion, right, is that the ants are probably looking the way they are because you have the disk there. The other interesting thing is that the host galaxies of the QPEs show some evidence for at least pre-existing AGN activity, even if it's in the past. But then also, of course, and as Thomas just showed us, there's a very, very strong connection between the QPE hosts and the TDE hosts. And so perhaps, even though the physics, of course, is very different, perhaps QPEs might give us an interesting context to understand ants being a very different phenomena. But, AGN plus TDE activity is contributing in both cases. And then, of course, we have the one example of a optical QPE, if you want to call it that, Assassin 14KO, which is potentially consistent with a repeating partial TDE, although a lot of people in this room have done work to understand it in more detail. And so I think these types of events are interesting, not necessarily because they're directly related, but they are helping us understand this much broader context of what are the nuclear transients happening in AGN host galaxies? How does the existence of an AGN disk interplay with any sort of stars that are very close to the center of the galaxy, close to the black hole? And so perhaps, on a broader scale, we can get some high-level interesting constraints from understanding these events and the ants in context. Thanks. And finally, I'm excited to introduce this class of extreme nuclear transients, or ENTs. So one of these is already known. This is ET 2021 LWX, which was identified by ZTF and has a few papers on it already. But I found two others by looking in Gaia data. And basically, these events are ants on steroids, if you will. They're extremely luminous at peak, reaching levels several magnitudes above a typical TDE or a typical ant. And they're also incredibly long-lived, with rises of a few hundred days and decays that are, in every case, except maybe the ZTF one here, still ongoing. And so, of course, these are very energetic events as well. If we look at the properties of the black bodies, and I'll say that they are well fit by black bodies, they're very similar in many ways to ants and TDEs. They're obviously more luminous, which is part of the selection here. And they have much higher mass black holes than a typical TDE would. But in terms of their radii and their temperatures, they're broadly consistent with a TDE or ant picture. Obviously, the higher luminosity means that for a given temperature, the radius must be larger. But they're showing similar temperature evolution. They're not cooling particularly. So again, it's not this case of exotic supernovae. We're seeing some form of exotic accretion onto a black hole. And so if we put them in this kind of space of peak absolute magnitude or peak luminosity on the y-axis and their characteristic timescale, we find that they sit in a region completely unpopulated by any other class of known transient. They're both more luminous and much longer lived. And of course, this means that their energies are quite high. The typical energy for these ents is somewhere around 10 to the 53 ergs, so crazy high, 100 supernovae, 100 TDEs worth of energy for a typical event. And their luminosities are only rivaled by the most luminous events like Assassin 15LH, or kind of the very, very upper end of other ants or other superluminous supernovae, or the featureless TDEs. And so just to come back to ants, now that I've talked about these slightly related events, I think some of the future ways that we can potentially begin to better understand them are on the left here. I just want to highlight two for the sake of time. I think one of them is high signal-to-noise UV spectra. We already see in comparing AGNs and TDEs in the UV that there's some interesting defining characteristics. The AGNs tend to show much stronger carbon lines and magnesium, which is almost never seen in TDE UV spectra, whereas the TDEs tend to show helium and strong nitrogen lines. And so potentially by obtaining a larger sample of UV spectra for ants, we can start to understand what's going on in the UV. Are they more consistent with an AGN or TDE? Obviously, this is complicated by the fact that you have an AGN in the first place. Perhaps this is one avenue towards understanding them better. And then another is the coronal lines that we've already heard about yesterday. And some of these ants, in particular on this plot at least, Assassin 18JD and 18DYK, do show coronal lines. And so potentially this is another interesting connection to the TDEs, as we heard for the coronal line emitters. But I think one of the interesting things for these coronal lines, both in the case of TDEs as well as ants, is potentially if we can understand the photoionization physics well enough, we can start to use them as a probe of this unobservable EUV SED and start to understand what's actually happening across the electromagnetic spectrum here. But there's obviously much more that can be done to understand these events in detail. And so with that, I'll just close by saying, I think we found an interesting class of transients in these ants, and that we should start paying more attention to events that are happening in AGNs. Whether or not it's easy to say that they're TDEs, I think, they're interesting events, they're happening, and so we should pay attention. But I do think that the rates and the observables of these events do seem to suggest that a very plausible explanation for at least some, if not the large majority of these ants, are TDEs occurring in AGNs. And so, there's obviously still a lot of work to be done, and one of the things in particular I'm interested in doing during this program is talking to some theorists about taking the connection of what we know about these simulations of TDEs and AGNs and trying to push that to at least some, better constraints on observables to actually compare to what we see in ants and know, are they at all consistent, or, what's going on with these events? And so with that, I'm happy to take any questions.
Go ahead.
Hi, yeah, thank you for that. I'm curious just if you had like any other follow-up on these ENTs, like, I don't know, spectra or anything else?
Yeah, so I should have mentioned, and I forgot, that we'll be submitting a paper. Sorry. I hope to be submitting a paper this coming week on them. And so we do have some spectra, and we find that they are, one of the problems is that they were identified somewhat late, and so we had the spectra relatively far after peak, at least a few hundred days in the rest frame. But we see for all of them broad magnesium emission, which is interesting. They do all seem to show some evidence, whether that's from host galaxy modeling and comparing the UV or X-rays with having a pre-existing AGN. But unfortunately, for most of them, we only have the one spectrum. We have no idea about the spectral evolution and things like that. But they are broadly similar in that they have broad lines, they have blue continua, things like that.
When you say broad, like how broad?
I think they're about 5 to 10,000 kilometers per second. So, consistent with AGNs or TDEs broadly.
Thank you.
Yeah, so one comment on the 2021 LWX, the scary Barbie one.
Yeah.
The X-ray, I got X-ray on that one, and it's hard since pre-peak. So there's never a soft component, it's always hard. And it's 10 to the 46 also in the X-rays early times.
Yeah, so this is also in the paper. I'm just showing a bit here, but we see that as well. I think that's interesting, and but again, right, we're looking at potentially much higher black hole masses, potentially pre-existing AGN. So it is possible that there is some corona there already. But as you said, this one is particularly hard. I think the photon index is even much harder than a gamma of 2. So that's a very interesting case on its own.
Yeah, and another thing, like between classifying TDEs and AGN, one of the things that people don't pay much attention, but it should be a pretty clear way to classify. It's hard to do, like time-consuming, taking spectra, but the broad lines in AGN are always realized. So there's always a correlation between the width of maximum and the luminosity. And that is the opposite relation you find in TDEs, because one is kinematic and the other is electron scattering.
Yeah.
So it's a good way to separate things.
I agree, except for the fact that it's not clear to me what would happen if you, say, had a pre-existing broadline region and then you had a TDE. What's the dominant component of the broadline?
Right, but if it continues to be virialized, then the electron scattering is not happening, because that would change how the
Sure, but right, the picture I'm suggesting for ants, right, is that potentially most of the mass and different, right, so you are potentially interacting with the disk, and so I think that's a fair point. It's just not clear to me how that would sit in terms of the, AGN virialization versus the TDE, electron scattering, which would actually be the dominant component in setting the width of the broad lines. But that's a really good point. It's something to look into.
Thanks for a really nice talk. I'm just wondering with the ants if you've looked at any, for any radio emission from the flares or from the hosts or anything.
Yeah, so I haven't. I remember your question from Australia, and I've tried to look.
Did I ask you the same question to the other
I think
time?
so.
Oh, I'm sorry.
It's a good question and absolutely something that should be done, but I haven't yet. And I think part of the problem is I don't know that too many of them have actually been followed up in the radio, and so I think we're just going to be stuck with whatever exists in surveys, which would be good enough to at least.
In the northern hemisphere, VLAS goes reasonably deep.
Yeah, sorry, I'm not trying to disparage surveys at all. It's just we wouldn't necessarily have particularly high cadence to know what's happening, but we could go look, and I think that's an interesting thing to go look and say, are they completely consistent with AGN-like radio emission throughout their evolution, or do we start to see a more radio TDE-like component after the flare starts? So yeah, super interesting, and looking forward to to looking into that.
Yeah, before asking my question, I would fully support any radio follow-up because you have 10 to 53 ergs. It's going to be any sort of a solar mass is going to get 0.1 C or more, so lots of radio to be expected. So my question, or really a comment, my question maybe is on the SED. So do you have the full SED of these events near the peak? Are they thermal?
For the ENTs in particular, for the
yeah,
ants?
for one of these, let's say.
We don't, unfortunately, for most of them, have the SED near peak. For the Gaia ones, it's somewhere down here. Where
you have multi-band. I would expect, since there's a pre-existing AGN, let's imagine there's a disk, now you have a optical emission, so there's a lot of reprocessing.
Yeah, and so for...
You should get, there's an extra emitting surface than the, let's say, maybe the optical photosphere. So you should get some red excess, let's say IR, or IR you already know, there's echo. But then in the redder bands, you should get, meaning it's a shallower than the religions, yeah, that's the expectation.
So, of course, unfortunately, we don't have particularly great coverage of that portion. So I should have, I didn't mention, these are all at redshift 1, roughly. And so all of the optical and UV stuff that we have is, the rest frame UV to the blue. And at least there it looks thermal, but I'm not sure that we have anything kind of approaching the near infrared besides the Ys, which is rest frame H and K. But here I think that's starting to get dominated by hot dust more than, the tail of whatever, transient emission.
Thanks.
Yeah, thanks for the nice talk. I'm curious for the extreme nuclear transients. Did you put them already on a graph with black hole mass versus some properties, or what? Do we know the masses from the broad lines pre-peak, or?
So we don't have any pre-peak observations of any of the galaxies. This one in particular doesn't have a detected host galaxy, and these two, there's no pre-peak spectroscopic observations. And given, Muriel's point, I'm not going to use the broad lines to try to attempt any mass measurement because we don't know if it's realized or not. So all the black hole constraints are just from galaxy scaling relations. So, half a dex uncertainty there. But yeah, certainly things to look into in terms of, I'm happy to talk more about what in particular would be interesting to look at.
Yeah, because also for disruption, tidal disruption in an AGN disk, you still have the Hill's mass to affect, right? So
sure. And so given the energies, though, we do have a relatively tight lower limit on the mass. So for 10 to the 53 ergs and 10% efficiency, that's about a solar mass and a half. And so we're assuming, or the most likely explanation for these, given the rates and the observables, is probably a disruption of a 5-ish solar mass star. And so that's the masses here are certainly consistent with being above the Hill's mass, especially given that uncertainty. But they're pretty close.
Yeah. Okay. Thanks.
Hi. So, did you have a question? DJ? Yeah.
Okay, sorry, I didn't hear my name. So, Jason, I can't tell which the other two transients are, but have you looked and searched for Rosetta counterparts before the outburst, and if not, Rosetta? So what I'm trying to get at is, at least in Assassin 18 EL, is one of the really neat aspects of that transient was that there was a corona before, something happened, and the corona was destroyed, and then it reforms again, right? So that's a really neat aspect to probe. So I'm just wondering if you looked at archival X-ray data, and if you did, if it's hard or not.
Yeah, so for this event, I think I'm going to wait to release the names until the paper comes out. For this event, there is pre-flare X-ray emission that's relatively hard, and that continues during the flare. For this source, there's a relatively unconstraining Rosette limit prior to the flare, but it's not detected in XRT at a limit of about an order of magnitude below the Rosette. And so I think the X-rays are a bit of a mixed bag here. The ones that are detected are relatively hard, which of course is not typical of normal TDEs, but these are already not normal TDEs. But yeah, I don't think we see any evidence for an 18EL like corona disappearance. But again, this is kind of one point prior to the flare, one point in the flare in most cases. It's limited follow-up for these events, unfortunately.
So I get very excited about this extreme nuclear transients because we have recently done some modeling of tidal disruption events of population 3 stars. Mm-hmm. And I find the luminosity you get and the evolution timescale is very consistent with our results. So, and also these POP3 stars are gigantic, so they can be disrupted by black holes with masses bigger than 10 to the 8 solar masses. So I wonder if you have spectroscopic follow-up of these events to see if they're metal poor or not.
Yeah, so we don't have any spectroscopic follow-up of the host galaxies at this point. We got spectra for these events late in the flare, but I think there's still at least a little bit above the host that would preclude any sort of measurement of metallicity from typical lines, or at least make that a little bit more uncertain. So that's something to look into. But again, these are kind of at Z of 1, and so they could be low metallicity, but it's probably not the population 3 stars, of course. But it's very encouraging that you're seeing similar things when we're suggesting that these are most likely to be massive star, intermediate mass star tidal disruptions.
Yeah, I think I heard there's some recent observational evidences saying they're like POP3 or even like POP2 mostly stars, like in some of the nearby galaxies. So I think there is a slight possibility.
Yeah, I'd be happy to talk more about that. Yeah. Thanks.
Okay, with that, let's thank our speaker.